Hello, my name is Miguel Godinez, and I will be presenting on two-factor authentication resilient to server compromise using mixed bandwidth devices. So let's begin. So the authors had two main goals for their paper. The first being that they wanted to design and implement multiple two-factor authentication mechanisms that could be improvements of traditional authentication mechanisms. And secondly, they want to evaluate the performance of these new two-factor authentication mechanisms in regard to their security, usability, and deployment. As we're all familiar with, most forms of user authentication use a combination of a username and a textual password. But many experiments have shown that when users given minimal constraints on their choice of passwords, that they tend to pick weak passwords that can be short and/or non-random. This is mainly due to the limitations of humans to remember longer, more randomized passwords. This is why they often select passwords that have some meaning to them, such as pets, favorite hobbies, street names, etc. But this gives attackers the opportunity to build a relatively small dictionary list of potential passwords to test in an offline attack. These kinds of attacks are very attractive to them because by compromising a server and gain access to stored solid password hashes, they can recover the passwords of users relatively easily. This can be especially harmful because many users tend to use the same password for multiple online services, which is why in order to improve security, many online services have started incorporating two-factor authentication, which is something that all Georgia Tech students and faculty will be very familiar with. So there are four types of devices that were considered in the paper. Type 1 devices do not need any data connectivity except to periodically synchronize its internal clock or counter with a server. They though must be able to display a short numerical or alphanumerical encoded message, such as a PIN. So there is an image of a hardware token that would be classified as a type 1 device. For these devices, the user will read the PIN and manually enter it into the client browser C. Because they are doing this manually, they are susceptible to eavesdropping by a shoulder server, and these devices are considered low bandwidth. Type 2 devices must have camera capabilities in order for the user to scan the browser screen when it displays an encoded message, such as a quick response or QR code. The way this works is that the user will position the device so that the camera can detect the QR code on the screen and thereby decode the message. The device then sends the decoded message or PIN response to the client in a similar way that Type 1 devices do. Though it should be noted that lower budget camera phones may not be able to ensure that QR codes with messages longer than 2 kilobytes can be reliably recognized and decoded in a consistent manner. Therefore, these devices can range from low to medium bandwidth. For Type 3 devices, they will have the same client-to-device capabilities as Type 2 devices, but they will have the added benefit of having a larger screen. And for Type 4 devices, they will be authenticated by shared keys that will be established in the device's initialization process using Wi-Fi or Bluetooth. And we'll be going over the main differences in the four devices in greater depth shortly. So there's a few ways that two-factor authentication can be implemented. The most basic kinds are time-based protocols, which are available to all the device types. One thing to note though about this, as I mentioned before, is that it relies on an internal clock or counter, which has to be synchronized with the server. And the main weakness of this protocol is that if an attacker can manipulate the device's internal clock or counter, then it could compromise its security. There's also symmetric and public key protocols that are available to Type 2 devices and higher. This is because they require the user's device to receive a challenge message from the client. And lastly, there's key encapsulation, which is a variant of the public key protocols, but it replaces the public key encryption process with key encapsulation. But it should be noted that this protocol is not as readily available, given that it requires certain cryptography algorithms that may not always be included in most cryptography libraries. So here's a quick list of some of the variables that will be abbreviated in the next few slides. Some are obvious, but the ones that we should take note of are S for device secret, Z for pin, TD and TS as the current time of a device or server, FK as the pseudo-random function, and O as a function that computes the amount of effort needed per password, usually in the context of attacks. Here we have a diagram of the low bandwidth pin mechanism. The user in this example would be in the possession of a Type 1 or higher device at the moment of authentication, and they would use that device, whether it's a authentication token such as the one we have in the bottom right, or it would be a smartphone that has an app that can generate the similar pin. And again, this pin will be computed based on the internal clock or counter that was synchronized with the server. And we have the equation of how the pin will be derived, and that is the device secret XORed with the pseudo-random functions of the current time. And so that pin will then be provided by the user manually, in addition to their username and password to be confirmed by the server. So here we have 3 images that were provided in the paper. On the left is the login page of the client. It displays the QR code. And in addition to the username and password, the user will have to input a verification code. And to do that, in the middle we have an image of the app on their smartphone that they use to scan the QR code. On the right we have that action being done, the camera focusing on the QR code, and then the app again will generate that pin that the user will then enter into the verification code portion of the login. Here we have diagrams for low bandwidth QR pin mechanisms that use symmetric key or public key encryption. In these mechanisms, the user's device will need to have a moderate amount of camera capability in order to capture the QR codes reliably. So again, the server will provide a challenge to the client. The client will display that as a QR code. The user will use their device to decode that X message, and then using its own device secret, it will do the XOR of it and the pseudo-random function of the X code, and this will provide the PIN. And so the user will then provide their username, password, and PIN to complete the authentication process. And that was for symmetric key encryption. For public key encryption, it would do a similar action to compute the PIN. It will use the device secret, and it will XOR that with essentially the random string R in order to retrieve that PIN And so they will provide the password and PIN to the client, which would be passed over to the server to complete the authentication process for public key encryption. On this slide, we have diagrams that represent the medium bandwidth QR mechanism. In both symmetric key and public key encryption, they will use two distinct QR codes. The first will mark in orange. And so, as before, the server will provide a challenge to the client. It will display that as a QR code, and this we're marking in orange. Then the device will decode that and re-encode it in its own QR code, which we'll mark in red. So then the user will have to position their device so that the front-facing terminal can read that QR code and thereby generate the necessary PIN to complete the authentication process. This image provides an example of full bandwidth Wi-Fi mechanism. And so we can see that in the back there is a login that requires a username, a password, and a verification code. And because this is the Wi-Fi mechanism, then there needs to be a bidirectional channel that is established between the device and the client. And we can see that happen in the first line of the pop-up window. Next, there'll be a challenge that'll be sent over from the domain to the client. The client will forward that to the device. The device will respond, and this response will be sent back to the domain. We can see that it's auto-populating the PIN necessary to complete the authentication process. And so this PIN can be a 128-bit or higher code. And so this is why it's considered the full bandwidth mechanism. And here we have the diagrams for the full bandwidth Wi-Fi, and Bluetooth mechanisms. The two diagrams are for symmetric key and public key. And both will require a bidirectional channel to be established between the device and the client, either using Wi-Fi or Bluetooth. And after that's been established, then it will send over its domain name and challenge. The devices, in either case, will respond with its computed PIN to the client, and then the client will pass that on in addition to any necessary parameters that are required for the authentication process. In these diagrams, we have the full bandwidth QR Bluetooth and QR Wi-Fi mechanisms. And the main difference between these and the previous mechanisms is that instead of having bidirectional communication between the device and the clients, we will instead use a QR code in a similar fashion as we demonstrated before to communicate between the client and the device. Then we will use a unidirectional channel to communicate the computed PIN from the device to the client over Wi-Fi or Bluetooth. Here we have a table with all of the different two-factor authentication mechanisms in the different columns. In the different rows, we have categories that they may fall into. So we have, for example, the timer challenge response, and this shows that the lower security mechanisms will use a time-based response. It shows the protocol types, and we can see that the higher security mechanisms will use a challenge-based response, as well as a symmetric key or public key protocol. And this again goes in line with the type of device that is required of each mechanism, with higher security mechanisms requiring a higher type of device. And then lastly, we have the user's effort. And this really shows the different processes that are required for each of the authentication mechanisms. So again, the lower security mechanisms will utilize just the PIN that's entered into the client, whether it's a traditional protocol or a time-based protocol. Or we can differentiate the two middle mechanisms. The low bandwidth QR pin mechanism using a single QR code that then is decoded into the pin, which is entered into the client, or the medium bandwidth QR mechanism that uses two separate QR codes in order to have added security. And then lastly, we have the full bandwidth mechanisms that can use either a bidirectional channel between the device and the client, or a unidirectional channel between the device and client, because the channel between the client and device will utilize a QR code. This table continues from the previous. In the first row, we have the size of pins. The low bandwidth mechanisms will have a pin size of 19 bits. The medium bandwidth mechanism will have a range between 20 and 128 bits. And then the full bandwidth mechanisms can have 128 bits or greater. The next row, we have the online attack success probability. This probability is indirectly proportional to the size of the pin. So the most secure mechanisms will be those with a higher pin size. The following row, we have offline attack overhead. This is essentially the number of hashes that an offline attacker would have to go through per dictionary size. And again, this is proportional to the pin size. So the higher the pin size in this case, the more hashes that an attacker would have to go through to crack essentially the user's password. Next, we have lunchtime security. Generally, all of them have some security against a lunchtime attack, except the traditional and the low bandwidth pin mechanisms, because they use an internal clock. If an attacker can manipulate that clock, then they could be compromised. Next, we have secure against lunchtime eavesdrop and server compromise. Again, the traditional and the low bandwidth pin are not secure against this, but the others would be if they use a public key encryption. And then we have the time sync question, and this relates again to whether they're using a time-based response. And then finally, we have the client software. All of them will use an HTML browser. The low bandwidth mechanisms will not require any special hardware. The medium bandwidth mechanism will require an additional webcam for the client terminal for that second QR code that will be displayed on the device. And then lastly, the full bandwidth mechanisms would require Wi-Fi. In this case, Bluetooth is implied to be a given for that level of device type. So the conclusions that the authors came to was that the mechanism that provided the highest level of security and usability was the full bandwidth Wi-Fi mechanism, with the next best being the full bandwidth Bluetooth mechanism. And both of these mechanisms would be based on the public key encryption. But if a malicious browser extension was a concern, then the authors recommended the full bandwidth QR Wi-Fi or QR Bluetooth mechanisms. And lastly, if time synchronization was available, but browser extensions were not, then the authors recommended the low bandwidth QR pin mechanism because it provided additional resilience to offline attacks while having the same advantages as the traditional two-factor authentication.